Hey guys, in this video I'm going to show you what should happen in the lab to get the data and how to find the acceleration due to gravity. I have a ball here, I have the dropping thing here, and so let's start data taking. That looks pretty good. And you can see that the data isn't fantastic. There's some problems here, maybe some problems here, but it should be enough for us to select the region. Now this region, it looks quadratic, but most importantly, it looks like only gravity is acting on it. So down here, it hits the thing. Up here, you can see a little bump. That's maybe where I dropped it. You want to select the region where only gravity is acting. And actually, I can cheat a little bit and see right here, the velocity seems to be going up, and so I really shouldn't include in the position that part at all. So let me try to do a little bit better job. I can match what I expect for both the velocity and the position. Okay. Now go up to Analyze, Curve Fit. I can pick AT squared plus DT plus C. Try fit. Those are my parameters right there, and I'm going to do the same thing down here. I want a linear fit.
So now that we've used Logger Pro to fit our curves, let's go over to the whiteboard and see how we can use these fits to find the acceleration due to gravity.
So the two equations that Logger Pro fit to our data are the following. The velocity is mt plus b, and the position is at squared plus bt plus c. Now where these equations came from there's two reasons for that. Under the acceleration due to gravity and only gravity, the velocity was a straight line, so we picked this, and the position was some kind of polynomial, so we picked this. Of course, the other reason is because these are exactly the kinematic equations that we've been learning about in class. Specifically, they are the final velocity is the acceleration times time plus the initial velocity, and the final position is 1/2 the acceleration times squared plus the initial velocity times time plus the initial position. So that means that we can directly associate the coefficient A with 1/2 times the acceleration, the coefficient B with the initial velocity, and the coefficient C with the initial position. And from the velocity part, we can say that the slope m is the acceleration, and the intercept b is the initial velocity. Oh, sorry, I used inconsistent notation. Let's write that as 0. So we have two different ways to find the acceleration. Of course, this acceleration now is the acceleration due to gravity g. Using the slope of the velocity, we can just immediately read off m is the gravitational constant, and for me it was negative 9.212 meters per second squared. And over here we have that the coefficient A is 1/2 times g, and for me my A was negative 4.64, so that means that my acceleration is 9.28. Okay, so that's not a perfect value, 9.28 and 9.212. Sorry, this is a negative right here. But these are pretty close to what we expect the acceleration due to gravity to actually be, of course, 9.81 meters per second squared. And I can look and say that, okay, well, the error on A was 0.0644. But of course, that 0.0644, that's just the error on the fit, so that the data which we told it to fit is well represented by a quadratic with an acceleration like that, but the actual value is not very close to the gravitational constant. So this is a case of a very high precision measurement that is not very accurate. Of course, in my case, I got 9.28 and 9.21 for the two values from the velocity and from the position. So in that sense, I'm pretty happy with my results. But of course, in your case, you just have to decide how you feel about your results relative to the device that we used in class.
This is, of course, much better than if we just did some estimate, like dropped some balls and try to time them ourselves. But of course, there's still some inherent uncertainty because this is a lab, and uncertainties are part of understanding how experimental science works. Thanks, guys.